In this video, I'm going to test the null hypothesis of equal mean height for males and females. Now, this might seem like a really obvious answer to a question because probably everyone would say, yeah, adult males are taller than adult females. But what's the effect size? And by answering the question, what is the effect size, you'll get some sense of what a large effect size is in nature. Because I would say that the difference between males and females is a large effect size, just based on my own intuitive sense. But then I'm going to finish off the video with a layered histogram so that you can see that even when the effect size is very large, there's still a lot of overlap between the distributions. So let's get to this one. I've got height measured in centimeters, and these data were simulated to correspond to a US Census study that was published a few years ago, not a really long time ago, but a few years ago. It's probably still fairly valid today. And I've got my gender variable where I've got to code it ones and something. I have to code it just any two numbers, to be honest with you. They could be any two. I tend to use zeros and ones to label two groups, but you can use ones and twos, or threes and eights, or 16s and 453. It doesn't really matter, as long as they're two separate categories in terms of numbers. And we can see that I've got females as 0 and males as 1. And because males have the larger number here, and we expect the mean to be larger for males, the t-value should be positive. Let's check that out. Let's go into Analyze, Compare Means, Independent Samples t-test. I've already got height in here and gender because I've already done this analysis, but it would look like this. Height, test variables, gender, grouping variable, and now I have to define the groups. And I have to put a 0 and a 1 because that's what the variables I used. If I put a 1 and a 2, it'll break down. SPSS will say something's wrong. So I have to put the numbers that I've actually used to code the two different groups. Click Continue and click OK. And here we've got the actual means. Again, this is consistent with the results associated with the US Census study. So on average, females are 162.81 centimeters tall, and the standard deviation is 6.99. Males, by comparison, are 176 on average, and a standard deviation of 7.42. So you'll recall that I have to assume homogeneity of variance for the independent sample t-test. If I violated that assumption, I wouldn't be too worried. But it has been satisfied here. So the amount of variability in female and male height is not statistically significantly different, with the Levene's F 0.556 and a p-value of 0.457. So I'm going to follow this equal variance as assumed row for the results, and I've got a t-value of negative 12.59. So I said actually the t-value should be positive, but actually it turns out negative because female is lower than male. So a negative 12.959 with degrees of freedom of 198. And we can see the p-value is less than 0.001. Here's the mean difference. The mean difference between males and females is 13.21 centimeters. So males are on average 13.21 centimeters taller. Now again, this is based on US Census data. Standard error of the difference is 1.019, and here we have the confidence intervals, negative 15.22 to negative 11.19. The next part I'm going to calculate here is the Cohens D estimate and also the Hedges G. As I mentioned in the textbook, we should arguably report Hedges G rather than Cohens D for a particular analysis because Hedges G is less biased. I created an Excel sheet for myself to create Cohens D and Hedges G because SPSS doesn't do it. And so what I have to input here is mean 1, mean 2, standard deviation 1, standard deviation 2, and then sample size for group 1 and sample size for group 2. So let's do that with the results of this study, and I'm going to calculate the effect size. So I've got mean 1, 162.81, mean 2, 176.02, standard deviation of 6.99, and the second standard deviation is 7.42, and I've got 100 people in each group, and I get a Cohens D of negative 1.83 and a Hedges G of basically the same thing, negative 1.83. So I guess the take-home message here is one, Cohens D and Hedges G do not differ very much, especially when the sample sizes are above 10 in each group, I would say. Here we've got 100, so it's clearly not very different at all. But the second thing is, this is the effect size associated with the difference between means for males and females in standardized form. So males are 1.8 standard deviations taller than females, With a negative Cohens D, you would say actually that females are 1.8 standard deviations shorter than males, but it's arbitrary whether I put the male or female mean first in the equation. So it's up to you. You can say one way or the other. 1.83 standard deviation taller than females, or 1.83 standard deviation shorter than males. And here's the formula I use to calculate that. So Cohens D is really easy to calculate in terms of inputting that into Excel. And this is in the textbook I have a correction factor here, and that is multiplied by the Cohens D value. So that is how you can get a little Excel function to calculate Cohens D and Hedges G for you. So the last thing I'm going to do here is create that layered or paneled histogram. So I'm going to go into Graphs, Legacy Dialogues, Histogram, and this is going to show me how much overlap there is between males and females, because even though on average males are taller than females, not all males are taller than all females. Let's actually look at what this looks like. Here we go. So this is what I essentially reported in the textbook. I probably won't clean this up actually. It's not really worth my time to do that. This looks fairly similar to what is reported in the textbook. And we can see that, let's say the mean for males is about right here, and the mean for females is about here. We can see there's still a very substantial amount of overlap between. So there are females over here that are taller, a little bit taller than the average height of a male. And we know that to be true just in our own experience. There are females out there who are 180 plus centimeters tall. In fact, there are some that are even taller. But with this sample size of 100, it didn't actually find any of those females. And for males, they're as short as 160-ish centimeters. Of course, there are some males that are even shorter. Again, this sample of 100 didn't detect those males. But the averages, the means here, I suspect would be very close to the means in the population. The standard error of the means are actually fairly small here. Sample size of 100 is not too bad to estimate the mean in the population. Of course, a larger sample size would be better, but 100 is not too bad. I do talk about that in the sampling chapter, about how 100 is really surprisingly good, especially if you have a random sample. So this is the demonstration of the test of the difference between males and female height based on census data. And I think it's a good example to show you what an effect size that is large represents. So males and females, it's a big effect. 1.8-ish standard deviation difference for Cohens D, Hedges G, but there's still a lot of overlap in the distributions. So even for a big effect size, there's still a lot of overlap.